In chapter 4, explaining motion, I talked about forces and how they affect the motion of objects. In this part of the lecture about rotation, I will discuss torque, which is the equivalent to force, but for rotational motion. So torque is the quantity that determines how an object will rotate. And it has the same effect as force for the linear motion of objects. Torque, tau, is the result of applying a force to an object that can rotate about a fixed axis. So what does that mean? So consider an object, just a random shaped slab that is fixed at this point and it can rotate about it. So if I applied some force F to this object, that will cause the object to rotate about this axis, like so. And so the application of this force results in torque, which causes that rotation. What is the definition of torque then in terms of that force? In order to write down the definition or the formula, we also need to know what is the distance from the axis of rotation to the line or the point where the force was applied. So the force was applied along this straight line, and therefore the distance from this straight line to the axis of rotation is that much. And so if I call this distance r, then the torque that is generated by the application of that force F will be equal to the product of the force and the distance from where the force was applied to the axis of rotation r. So the torque tau is equal to the product of the force and the distance from where the force was applied on the object to the axis of rotation. The units are the units of force times the units of distance, so this is Newton meters. For the torque generated by this force, the magnitude of the torque depends on several different parameters, meaning how far away from the axis of rotation this force was applied, or how exactly was this force applied with respect to the axis of rotation. Or in other words, what was the direction of the force when the force was applied to the object. Let's illustrate that with several drawings. So consider a simple door, and this is a top view of the door, this is the hinge. So let's apply force F at the very end of the door, and the force is applied perpendicular to the door. The distance from the hinge to the end of the door here is R. Okay, so the torque that's generated here in this particular example is simply the product of the force and the distance from the axis of rotation, which is located at the hinge. And so the torque is the force times the distance. Okay, now let's have the exact same configuration, but this time I'm going to place the force at a different position. So here is the door again. That's the hinge. Now the force is applied halfway the length of the door. So now the distance from the axis of rotation to where the force was applied is just that much. In this case, the torque is different. The torque, let's call it tau prime, will be equal to the product of the force. And let's call the distance here r prime. So r prime. Well, since the new distance from the axis of rotation to where the force was applied is half the original distance, that means that this torque will be 1/2 of the original torque. So when the length of arm or torque arm, which is the distance between the point where the force was applied in the axis of rotation, when this torque arm length changes, that changes the torque if the force remains constant. Now I can achieve the same torque for this example as for the previous example if I doubled the force, because I halved the distance from the axis of rotation. So that would compensate for the shorter distance. Another consideration into how big the torque is the direction at which the force is pointing. So again, using the example with the door. So here is my door. This is the hinge. Now the force is not applied perpendicular to the door, but let's say it's applied directly towards the hinge. In this case, the torque will be equal to 0. And why is that? Well, because there is no actual distance in the sense as those previous two examples from the point where the force was applied to the axis of rotation. So the point where the force was applied to the axis of rotation here, there is no such distance because the force and this line here that connects to the hinge, they are parallel to each other. And so you know, hope maybe from personal experience, if you push against the door in that direction towards the hinges, this door is not going to rotate. That is because this force acts along the line that starts from the axis of rotation and ends at the point where the force was applied. So in this particular configuration, there will be no rotation, no torque. There is another possibility for how the force was applied to the door, and that would be at some angle like so. So we know from, again, experience that the door will rotate. However, if you compare the speed of rotation of the door when we have this configuration of the applied force versus this configuration of the applied force, you would find out that here the door will rotate slower compared to here, which means that the torque that's generated by the force applied like so to the door is less than the torque in the first example. The reason for that is because since the force is angled to the door, part of the force actually acts parallel to the door and generates no torque, and then another part of the force acts perpendicular to the door and that generates torque, but that is less than the entire force. So therefore the torque in this case is less. So one more time, it is for the magnitude of the generated torque, it's important how big the force is, how big the torque arm is, or that is the distance from the axis of rotation to the point where the force was applied. And also, at what angle is the force directed with respect to the torque arm. And here in this particular example, the last example, the torque arm is this. For our purposes, for our course, we of course are going to deal with nice situations where the force is perpendicular to the torque arm, and so we don't need to deal with situations like that where angles are involved. And if we encounter a situation like this one, like this example, then we know that the torque will be 0. As I stated, torque for rotational motion plays the same role as force for linear motion, which means that I can restate Newton's second law for rotation by simply replacing the terms in the statement of the second law. Instead of velocity, I will use angular velocity, and instead of force, I'm going to use torque. So the statement of the second law then becomes the angular velocity of a rigid object remains constant unless acted on by an unbalanced torque. So that means that if an object is fixed to rotate about a fixed point, but it's at rest, it will never start to rotate unless, on its own, unless unbalanced torque is generated by applying some force. Furthermore, if an object is already rotating with certain angular velocity, this angular velocity can only change if an unbalanced torque acts on the object, which means some force is applied to generate the torque. Now I can also state the second law slightly differently. We know that Newton's second law was the link between force, mass, and acceleration. And so this statement of the law applies for linear motion. So then what would be the statement for rotational motion? Well, we know that the equivalent to force for rotational motion is the torque. Instead of linear acceleration for rotation, we have angular acceleration alpha. So the only thing that we do not know yet is what's the equivalent to mass for rotational motion. So this is what we need to know. So for rotational motion, torque must be equal to the product of a quantity that we haven't discussed yet and the angular acceleration of rotation. Well, this unknown quantity is called moment of inertia. So moment of inertia which we are going to label with capital I, is a quantity which depends on the mass distribution inside a rigid body. And this quantity, the moment of inertia, plays the same role as mass plays for linear motion, but for rotational motion. So moment of inertia is equivalent to mass for rotational motion. So it is not the same as mass because it is the mass distribution inside the rigid body, but plays the same role. So what does mass distribution mean? It means how exactly is the mass of this object distributed with respect to the selected axis of rotation. So for example, if you consider a dumbbell which consists of two masses connected with a thin rod, let's say if I have my axis of rotation passing straight through the center of this assembly, then the mass distribution is dictated by where the two masses are with respect to the axis of rotation. If I look at the same dumbbell, but now I select my axis of rotation to pass through one of the two masses, then you can see, and this is intuitive, that the mass distribution here will be different, and so this dumbbell in that second example will rotate differently compared to the dumbbell in the first example. This is only due to the fact that the moment of inertia is different for this selection of axis of rotation versus this selection of axis of rotation. And so, Newton's second law for rotation states that torque is equal to the moment of inertia times the angular acceleration. So this is the second law for rotation. I must make a correction. At the very top here, this is not the second law, this would be the first law. So, let's recap. The first law states that the angular velocity of a rigid object remains constant unless acted on by an unbalanced torque. And then for the second law, we have that the torque acting on an object is equal to the product of the moment of inertia of that object times the angular acceleration of that object. If we are going to make parallels between the statement of the second law for linear motion and rotational motion, force for linear motion is the same as torque for rotational motion. Mass for linear motion is the same as moment of inertia for linear motion. And acceleration for linear motion is the same as angular acceleration for linear motion, for rotational motion. Let's do an example problem. A wrench is used to tighten a bolt. What torque is generated by the wrench if 20 newtons of force is applied 25 centimeters from the bolt? So let's see what we know. We know the force that's applied, so that is 20 newtons. We know the torque arm, which is the distance from where the force is applied to the axis of rotation, so that is R, which is 25 centimeters. We want to find the torque generated by that force. So torque by definition is the product of force and distance to the axis of rotation from where the force was applied. So that would be 20 newtons times 25 centimeters. However, keep in mind or remember that the units for torque were Newton meters, which then tells us that the force must be in newtons and the distance, or the torque arm, must be in meters. Well, here the torque arm is in centimeters, so before calculating the result I must do a conversion. And so this becomes 20 newtons times 0.25 meters, which is equal to 5 Newton meters.